Hello guys, welcome back to our video on the refinery operation. Alright, so this video we are going to be talking about crude transfer operation and pump performance in the refinery system. Okay, so I think in our previous videos we've been trying to demonstrate how to carry out crude transfer operation from one tank to another. I think we started with transfer operation from our trucks down to our storage tank, and then in another video we carried out transfer operation from our crude storage tank to our feeder tank. Now in that video I think we used transfer by gravity without a pump, so that was done. Now in this video we're going to look at transfer operation from our feeder tank, which is our crude tank for processing, down to the processing skid. Okay, so this activity is actually carried out when we want to start up operation. So this is one of the activities, but in this video we are not going to be talking about the startup procedures. All we want to do is just to demonstrate how we can actually transfer crude to the processing units using the pump. But then we are not going to our CDU. We are just going to explain because the essence of this video is actually to talk about the pump performance, okay, now, and the operating zones of the pump. So we're going to explain more about the pump, and we're going to explain more about control valves. So the pump and then the control valve dynamics and how we interact with the pump. That is the main essence of this video. And also we're going to cap it up with talking about the pressure profile and also temperature effects. Then we can just add something like FIQ on it. So these are the things we're going to be learning in this video. So let me just let's go to the simulator so I can show you what we're actually going to be doing in this video. All right, so I believe we've seen it before. So this is our DCS simulator, and this is built with Excel. It's programmed and everything is actually working exactly the way it works in a refinery. The only difference is that we are not having transmitters hook up to this. Everything is done by programming. Okay, so like we said, we are going to be looking at transfer operation from our feeder tank down to our processing skid. And if you look at this screen, we see a tank here, 305. Now this V305 is actually our feeder tank, and then we have two pumps here. If you follow the line, you see that they are connected to this pump. Now these two pumps are sending the crude down to the processing device. Okay, now if you come over to the furnace tab, you see this tab is for furnace, but like I said, we are not going to be talking about the heating section of this. We are talking about just the transfer section. Okay, so we are not going to enter the preheating aspect before the heating aspect. So we're just going to stop in this area here. Okay, so we have the PT here, we have the TT, and as you can see, we have FIC, which is showing 0 kilogram per hour currently. We have the control valve, which has the FC. FC means free close. When there is a failure in the air supply to the system, it means the valve should what? The valve should close. That's what it means. Okay, and we have here the percentage opening is 43% open, although the pump is also, there's no flow, as you can see, 0 kilogram per hour. Then we have the FIQ here. So these are what we want to actually discuss about. So this, with respect to the pump performance, is what we are going to be talking about in this video. Now often, control room operators, this video is actually for control room operators. Yeah, now control room operators are actually trained to carry out these operations: open on pump, open valve, close valve, monitor parameters and try to balance everything. But then the question now is, there are some limitations to the knowledge that the control room operator is actually getting, right? When it comes to the pump performance, for example, we only know that we put on the pump and then we use the control valves to actually control the flow of what is going to our system. All right, we try to balance the level, and that is exactly the idea that is being taught to control operators, to balance these levels to ensure that the temperature and pressure don't exceed the maximum range. These are what we do. But then we need to go deeper. So the essence of this video is actually to to bridge a gap, to try to bridge a gap, the technical ideas, so that but just for you to have a different idea of what is actually going on when the pump is powered on. And then also when you are trying to open a control valve, you need to understand the idea, what effect is it giving to the pump. Okay, so these are what we're going to be learning in this video. Now we're going to start with a demonstration. So after the demonstration, we can now look at all the parameters, and then we'll try to explain how those parameters are actually being developed. All right, so that is what you're going to be doing currently. Okay, so if you've been following up with our previous videos, you know that before you carry out crude transfer operation, the first thing you need to do is to do your lineup. Okay, now what do I mean by lineup? Lineup simply means that we confirm that all our lines are properly in conformity with what we want to do. So let's say we want to carry out crude intertank transfer, and then we know that we are using our discharge line, which is this other line without the shutdown valve. Okay, so you trace the line and ensure that everything is properly lined up. Now from the control room, we are not seeing any valve going to the pump, but in the field there are manual valves. Okay, so you call the the field operators, and then you ask them to line up, right? That you want to carry out so operations, so they need to line up to ensure that everything is properly lined up. So when they go to the field, there is a terminal valve here. So they open the terminal valve, and then they follow the lineup. There are going to be various valves along this line. Since we have connection from these two tanks, definitely there is going to be a manual valve here. So that manual valve is going to be open, and then the one going to this tank is going to be closed. One going to this other tank is going to be closed. So they also follow up, and then they get to the pump. Now from the suction part of the pump, they ensure that we have flow, so they can open the drain to ensure that we have crude coming out before they can close the drain again. Now they follow the line up to the tank. The suction valve should be open, and then, but first of all, the discharge valve should be closed. I will tell you why, during the course of this video. We'll look into this. Okay, now this is the lineup. Now when they ensure that everything is properly lined up, you can now tell them to open. You can now tell them to power on the pump. So first of all, you ask them, confirm we are properly lined up. They said yes. So you can now inform them, tell them to put on the pump. Now the pump can be put on in two ways, either from the control room or from the field. It depends on how it's being programmed. Okay, now from this our programming, we are going to put on the pump from the control room here. Okay, so before we do that, I just wanted to first of all check around again. Now we see all our parameters. All right, so okay, let's go back. So we have two pumps. One of them is going to be on standby, while the other one is going to be in operation. So depending on previous operation and which one you think is okay for using, you can actually decide to use anyone. So let's zoom in. So we can go for the B. Okay, depending on which one you want to go with. So all you need to do is you power on the pump from here. So I click on, and then I go over to this other tab for the furnace. Now notice what we have here. Okay, now currently the pump is running. The valve, you see the control valve is at 10% open, and now you see the temperature has gone up to 44 degrees, which is a bit high. Now we are going to know why this temperature went up, and you see the pressure is at 1.2415 MPa, and then the flow rate is at 33,156 kilogram per hour. All right, now let's increase the percentage opening of the valve, and let's see how the parameters will change. So I click on this guy and I change it to 20%. So 20%. Now you see the temperature has gone down to 40 degrees Celsius. The pressure has gone up a little bit to 1.234, while the flow rate has gone up to 66,313 kilograms per hour. Now you can see our FIQ is continuously monitoring what is passing through the pipe. Okay, monitoring what is passing through and calculating it and giving you the answer there. We are still here. Now I will open again to 40%. Don't forget to observe what we have here: the temperature, the pressure, the flow rate. So if I increase to 40% open, okay, you see here temperature has gone down to 36 degrees. So this means that the more you open the control valve, we have more flow. So because of that, the restriction on the line is not that high. So due to that factor, the temperature will gradually be coming down. Okay, so that's what is going on here. Now the flow rate is actually going up because the more you open, the more we have a lot of flow coming into the line. Okay, so let's still continue. Let's open it to 60% and let's check. So by 60% open, temperature has gone up to 34 degrees, which is at room temperature now. Okay, so the operation is smooth currently right now. Now this means that when you pound your pump, you don't need your control valve to be too low. If your control valve is open at 10%, it's going to be, restricting the flow of crude on the line. Now that restriction is going to cause a temperature build-up at the pump and on the line. And if you continue to keep this valve at this particular percentage, it's going to damage the pump. The impellers of the pump are going to wear out. We are going to we are going to talk about the pump in this video. We are going to talk more about the pump in this video. But for now, we are demonstrating a live scenario. So yeah, I'm just trying to make you understand what is going on here. Okay, now you see the flow is about 198,000 currently now. Okay, so we can still take it up to 70%, and then when you click OK, alright, so you see everything has changed again. Temperature is still at 34 degrees because currently right now the line is very free. The restriction is minimum, and so the temperature is at the barest minimum. Alright, so this is our practical demonstration of this scenario. Now with this, we are going to explain what actually is going on inside the pump. Okay, we are going to explain all this for you to actually understand. All right. Okay, so let's go back. So as you can see, our FIQ has gotten up to 164 barrel per day and still counting. Okay, if you come back to the pump, you see this one is a liter per second, and the liter per second is also recording what is passing through the line, liter per second. Now for the FIQ, we have a reset button, so we can reset it. So let's say you want to commence operation for the day. Before you commence operation, you can actually zero it. You see it? You can actually zero it so that it starts from the beginning. Okay, so let's put up the pump. So you can see the pump is powered off. Alright, so now you see everything has gone back to normal. Now our valve is still 70% open, and then our FIQ is 171. Now before you start up your operation during the day, you can actually zero trim everything to make the FIQ zero, so that you can actually start counting from that particular day. So if you click here, you see you can get this to zero, and it will start from zero. All right, and what else? We can decide to use this to reduce and increase the control valve. Okay, let me do this again. So this time around, let's use the A. So I put on A. All right, so notice our LT 30201. Notice it's going down gradually, and notice the level coming down gradually too from here. All right, So notice our FI flow indicator is also giving us our reading. Let's come down here. We are 10%, so I will take it up again. Let's go to 60 and let's click OK, and you see our level has gone up again. So basically this is how to carry out transfer operation from our crude tank down to the processing unit. Like I said, I am not going to talk about this other part for now. I'm not talking about this other part for now because you see currently our furnace is down. The temperature is 30 degrees, everything is down. So later on in the future I'll put on the furnace for you to see, and also go to other tabs where we have the distillation tower, we have stripper, we have a lot of things to talk about, so do that. But for this video we are currently talking about the pump, crude transfer and pump performance. Okay, so let's stop this operation so we can talk more about our pump performance. All right, so the pump is currently powered off. Okay, so now let's talk about the pump performance. Okay, now when talking about pump performance, there are two very good parameters that we need to understand: the pump head and the flow rate. So these are what we need to actually understand. Now let's look at this curve. Now this is what they call the pump curve. Okay, so I believe a lot of us we've seen this curve already, and we already know what is there on this curve. But let me just emphasize the point here. So if you look at the curve critically, you see we have this this green line. Now this line is the pump head versus the flow rates. Okay, and this is exactly what we are going to be discussing here. Although we have other important things that we're going to talk about. We have the BEP, which is the best efficiency points. As you can see, we have the peak efficiency points here at this part here. Now there is an efficiency point where we need to actually understand that our pump should operate within, and that is this curve you're seeing here. And also we have the brake horse power. Okay, so that's talking about the horsepower, the power of the pump. Okay, so we also look at that. So in order to understand this, I need also to explain what we mean by the pump head. Okay, so the pump head is, like we know, when you put on the pump is actually exerting a particular force on the fluid for the fluid to move. Because why do we need a pump? For example, now if we have a tank that is filled with crude, just like we have a tank in this, and then if our pipe is just on the floor, there is no need for a pump. Once you open the valves, definitely the fluid is going to move, to the location. But then when there is an elevation, that we need to push, we need the crude to go up to, it means we need something to push the fluid to actually move. So what is actually doing that is the pump. Now the pump head is the sum of the total energy that is needed to impart that flow on the fluid. So that is the pump head. Okay, so the total energy, now we're talking about energy, we know we have kinetic energy, we know we have potential energy. So the sum of these energies is what makes up what we call the head. Now I don't know, okay, let's just give a little, I will use this tab here, let me just include a blackboard. So let me just draw something that will represent a blackboard. Okay, and let me change it to black. All right, so I just want to demonstrate how we can actually obtain the pump head. Okay, so let's say we have a pump. This is a pump. We have the suction line. The suction line is the line that comes to the pump, and then we have the discharge line that that is the output of where we are trying to send the fluid to. Okay, so here's the suction, here is the discharge. Okay, now let's use Bernoulli's equation to actually explain this. Now, according to Bernoulli's equation, we have that the pressure at the suction side, or let's say if you're looking at the flow from one end to another end, so we have the flow from number one and the flow from number two, but this time around you're using suction and discharge now. So the flow, the pressure from the suction side, which is S, plus the kinetic energy, which is half of the density, and the velocity, right, at the suction side, plus the potential energy, which is the density multiplied by the gravity, right? And then we now talk about the height, which is the H at the suction side. Okay, now this is going to be equal to the one at the output. So we are talking about the pressure at the discharge plus the kinetic energy at the discharge. So we have half of the density and the velocity square of the discharge, which is d, plus we have the density, gravity, and the height at the discharge. Okay, sorry, it's not very smooth. I'm using my mouse to actually draw this. I don't have a pen for now, so maybe I'll get a pen later. All right, now this is actually giving us the statements of the movement of the fluid from one location to another location in a pipeline. Okay, now let's refer this in terms of the power output. Okay, so looking at the power output now, so let's say the power output is going to be the summation of these 2 points. So we are looking at P of the discharge, so we are looking at the output minus the input, minus P of the suction, you can close the bracket here, plus the kinetic energy at the V square D, which is the discharge, minus V square at the suction. This is square here. Okay, close this bracket, and then we look at the height. Okay, which is the potential energy. So plus rho g into brackets height of the discharge and the height at the suction. So when we talk about height, you know, we are talking about the heights of the elevation at the suction side. Okay, so the tank elevation in terms of the what's it called, the pipe inlets to the tank, so the height of the pipe inlet to the tank, and also the elevation of where our fluid is going to. You know, just imagine the fluid is going into our distillation tower, and the distillation tower, the inlet is at the middle of the tower, sometimes about let's say 10 meters high, 16 meters high, 20 to 30 meters high. Okay, so meanwhile the suction is about, let's say, 5 meters high. So if you are pushing a fluid from 5 meters high to about 30 meters high, you know, we need a lot of energy to do that. So which is what we are trying to get here. Now on getting this, let's now convert this to our head. Okay, so the pump head is now equal to, so what we do here is we divide the right hand side by rho g. Okay, so when we do that, we have pressure at the discharge minus the one at the suction divided by rho g plus if you cancel the density out, so we have V at the discharge square minus V at the suction square all over 2G. This will be plus, this will cancel out, so we just have the height here, height at the discharge minus height at the suction. All right, so this is the formula for the pump head. Okay, but let's hold on. You know, when talking about, you know, the flow in a fluid, we can't actually forget talking about the losses. Okay, because inside the pipe there are, you know, there are things that make restrict the flow of the fluid. All right, so due to maybe the roughness of the pipe and also the fittings. So, you know, we have valves, and those valves have some, you know, some from the connections, there are some parts that will prevent flow. Okay, because there is not very smooth. Anywhere there is a connection, that area is not very smooth, so it's going to prevent the flow. And also we have bends. Okay, so you just imagine a fluid coming in and then going up like this, or let's say like this, it come here and it go here. So immediately it hits this ending here, there is going to be a restriction. The flow will reduce. Okay, so these bends are also losses. Okay, so these are going to also be factored into this calculation. So we can add the losses at the suction side and also at the discharge side. So we just have the head loss at the discharge plus head loss at the suction. All right, now this is actually the formula for you to calculate your head loss. Now you need to understand one thing again. We are talking about energy, right? We have kinetic energy and potential energy. So the energy that is imparted on the fluid for you to move, for you to push it, for the fluid to move from one location to a particular height and to enter into a given location, is what we call the pump head. Okay, now the head losses are very, very important. Don't forget, when you try to close a valve, something goes into the pipe to prevent a flow. That is a head loss. That is a loss. Okay, now that loss is what is reducing the flow rate on that line. What the valve closure we do is, there is a ball that goes into the pipeline to block the flow of this thing. It's called a trim. Now the assembly of the valve, where it actually functions in the closure and opening of the control valve, is called a trim. We are going to look at the trim very soon. So okay, so let me clean this, and so we can move forward. So I'll come here and I will just delete everything. All right, so let's go back. Let's go back to this aspect. Okay, now that you understand the pump head, now during how do you select a particular pump is also very important. So I know this is not a design class, but I think it's also good that we understand how we come about selecting a particular pump. Okay, so we'll start by looking at the design stage. Okay, now during design, or let's say during the preliminary design, a plan has already been put in place that, okay, we need to actually design a plant that we can be getting, that we can be refining, let's say 30,000 barrels per day. Okay, now that's the plan. So during simulation, you use the Aspenisis or any other simulation tool to carry out your simulation. Your flow rate is going to be 30,000 barrels. Okay, now using a flow rate, you simulate, and then you get your products, and then everything is fine. Now after the simulation, the PNID is drafted, or let's say you start from PFD before you get your PNID. So the PFD is drafted, the PNID is also drafted. Now during the PNID, a lot of manual valves and control valves will be incorporated into the design. Now all those manual valves we are not factored in during the simulation, right? But then the capacity of the plant is already designed to operate at 30,000 barrels. Okay, now after the P&ID design, the piping engineers will draft out the 3D model of the plant. Now mind you, the 3D model of the plant now shows you the route that the pipes and everything will be, and also the location of the pump. So that is when calculations can be done. Now calculations can be done to obtain the pump head, okay, due to the number of bends, the number of valves that will be on the line, the elevation of the line, and all the rest from the discharge and also the suction. Now when this calculation is done, the head will be obtained based on the formula we just calculated here. Okay, so the head will be obtained. Now when the head is obtained, for example, let's say the head is 100 meters. Okay, and let's say the head is 100 meters, and we already know that our plant is designed for 30,000 barrels. So what the designers will do, they will take these two parameters, the flow rate, which is 30,000 barrels, and then the head, which is 100 meters, and they will send it to a manufacturer, a pump manufacturer. Now the pump manufacturer, they've done a lot of tests already, and then they have pump curves. They have what we call pump curves, so which is what I showed you here. They have pump curve, so something like this. Now this pump curve is now telling us that, okay, at this particular head we are going to have this particular flow rate. So take for example this pump curve. Now you see we have 100 meters as a head here, and if you trace it down, you see when it meets the head, if you come down, you're having about 30, let's say 32.5, let's say 32,500 500 barrels per day. So we can take it back. So let's say the pump head should be around 110 meters. So with this we can get here. Alright, so if our pump head is 110, then we know our flow rate is going to be this 30,000 barrel per day. So this is what we mean by pump head. So when you look at the pump curve, and then you notice that the pump head is meeting up with your flow rate, then you cannot accept the particular pump. So this is how pump selection is carried out from design down to the manufacturers, and then selecting the actual pump that you're going to be using in your facility. Okay, so with this you can now see here that, so let me delete this. All right, so now we understand how pumps have been selected. Okay, so the next thing we're going to talk about is the pump is selected, and then we have the pump installed in our facility. So what effect is the control valve going to be playing on the pump? So we are going to look at that, because if you look at this, this pump curve, you notice that we have three lines here. Now this green line is showing that we have what we call normal operation. So this is normal operation here. This is a throttle value, and this is what we call a run out. Okay, so this is when the valve is widely open. When the valve is 100% open, this is what you're going to be getting, and this is called a run out. A run out means it has exceeded the what's it called, the pump curve, the pump head. Sorry, it has exceeded the pump head. As you can see, it's going this way. Okay, so this is a run out. Now this is not acceptable. Okay, so it means opening of the valve actually affects our pump head. So this is what it does. Now once the pump head is affected, it affects also the flow rate. You see from here, you see the flow rate, and then for this head you see our flow rate, and this head you see our flow. So the flow rate reduces with increase in pump head. Flow rate increases with an increase in pump head. And what increases our pump head is restriction. So the more we have restriction on the line, the more the pump head goes up, and the more the pump head goes up, the more the flow reduces, and it gets to a particular point where it's critical that we cannot operate. And also, if you open the valve to a particular extent, it also gets to a critical level that we cannot also operate. So we will come into that. So first of all, let's look at the control valve and how it affects our pump operation. So let's take this out. Okay, so something I forgot to mention is I think I said I'm going to explain why we need our discharge valve to be closed when we want to put on our pump. Okay, but before we talk about that, yes, let's look at these valve characteristics. Okay, so I've mentioned quick opening, I've mentioned linear, and I've mentioned quick equal percentage. Okay, now if you look at the opening here, you know, we are talking about, I drew the drawing for the trim of the control valve, and I mentioned that it's a configuration where the opening of the valve. So if you look at this, you see this first one is the quick opening. You see it. So this is a rectangle. So immediately you open it, we have a lot of flow going inside. Now for this other one, you see it. This is linear. So the one for linear is this one here. So the opening is going to go linearly, and then for quick opening, this is how it is configured. Okay, so these are the openings. This is the difference between these guys: quick opening, linear, and then equal percentage. So this opening is the configuration for the trim, and this is what makes the opening vary from one control valve to another. Okay, so going back to our pump. Let me clean this. So going back to our pump, we are talking about why we need to close the discharge of the pump before you put on the pump. So here you see, for this diagram, this line here is showing that the valve was actually completely open before the pump was powered on. Now what happens is that we have a lot of flow will just go into the line at once. And don't forget that, you know, the pump is supposed to balance between the suction side and the discharge. Okay, so if the pump takes a lot of fluid out and there is nothing for it to circulate, it's going to cavitate, it's going to, you know, start making noise, and it's going to affect the operation of the pump. Okay, so what it means is that you need to actually close the discharge of the valve, and then when you put on the pump, you know, we have a lot of fluid inside the pump, then you can start opening it gradually. Okay, now that gradual opening is going to, you know, enable the pump gradually increase its flow. All right, so this is also what you need to know as an operator, that you don't need to open the discharge of the valve before you put on the pump. The discharge of the valve should be closed, and when you put on the pump, you gradually open it by checking the pressure. Now don't forget, the pressure you're checking at the pressure gauge is the head of the pump. So if the head falls down, it means there is no flow. So if the head falls down, it means you've gotten to the run out. This is, so you need to adjust it back. Okay, so that is that. Okay, so now let's look at the control valve. So we all know that the control valve, like what we have here, is the regulator of the flow. So I think I've demonstrated now. When you open the control valve, you have more flow going in. So this means that the control valve is the regulator of the flow that enters our line. Okay, but then what is the significance of this, of what the control valve is doing? Now if you go back to the formula that we did, we notice that you see the head loss. This is the head loss at the discharge side of it. Now, the more you increase this head loss, what is going to happen? What will happen is that when you increase the head loss, because you're adding this head loss, and then it's going to increase the head of the pump. Okay, so and we know that when the head is increasing, the flow is reducing. Okay, so let me just go here. Let's go here. So let's say we have we have a pipe, right? This is our pump. This is our pump here. This is our suction part. Now we have a control valve here. Let's just use this as a control valve. So this is our control valve. Now this is our so there is a stem, yes, what we call a stem inside here, and this region you're seeing, this part you're seeing is what we call the trim. We call here the trim. Okay, here is a trim. Now this is a stem that has something like a ball that opens and closes, you know, to actually to close the line or to open the line. So that's what we have here. Now this thing we call the trim is what has a design of an opening. So this is a design of an opening here. A design of an opening here. A setup that allows the flow to open in a given ratio. Okay, they call it flow coefficients. Okay, so that's a CV. All right, so this is how a CV is obtained and calculated. Now, like I said, this is the trim. Now this is a ball, or it depends if it is a ball, or depend on the type of this thing that will be here, the regulator that will be here. Okay, and here is a stem that goes into the diaphragm. So this is a diaphragm. We can have a manual. We can have a hand wheel here. So this can be in two ways, either with the hand wheel or with the diaphragm, using the control from the control room. Okay, so whichever way. Now, what I want to explain here is that we are talking about control valve. So we have a flow of fluid coming to this part, right? Now, if the valve is open 100%, it means a lot amount of fluid we just go through. Okay, but then if there is a restriction, the flow will accumulate here. There will be an accumulation of flow here. Okay, so without, there is a reduction. If it is totally closed, it means there is nothing going through. But if it is open a little percent, we have a little flow of fluid coming out here. If you open it more, we have more coming out. If you open it more, we have more coming out here. Okay, now what is the trim? What is its trim? There are three types of there are three characteristics or three types of trim. I think in one of my posts on LinkedIn I mentioned about this. So let's just go to LinkedIn. Let me just show you this. So yeah, okay, so this is a post. I talked about control valve characteristics, and if you see here, we have different types of opening, which is for the trim. Now we have the quick opening, we have the linear opening, and we have the equal percentage. So it depends on the kind of trim that you're using for your control valve. That's how the flow will actually be regulated. Okay, so let's look at the first one. The first one is the quick opening. So quick opening control valves have a CV that increases rapidly as the valve is opened. So immediately you open Immediately you open the valve for this quick opening, immediately you open the valve, there's a rapid flow of fluid. All right. Now, in some settings, you might actually want that. Maybe if you are transferring water to somewhere, you might want water to just pass through. But then when we are trying to control a process that requires a gradual increase, we don't need this. Now they provide a large flow rate for a relatively small change. So if immediately you open it small, there is going to be a large flow. Now this characteristics is useful for application where the valve needs to open rapidly to allow a surge of flow. Okay, so the second one is a linear. So when you know the name linear, you know that as the flow, so you have the control valve opening, there is a linear flow, a linear flow. So the linear is a control valve that has a CV and increases proportionally with the valve position. In other words, for every 10% increase in the valve opening, the flow rate increases by 10%. This characteristics is suited for applications where a direct relationship between valve position and flow rate is desired. So the last one is equal percentage. So equal percentage is one of let's say is one of the characteristics that is mostly used in oil and gas. So most of the valves for crude line, diesel line, naphtha lines, most of them use equal percentage. Now let's explain and let's see why we are using this. Equal percentage control valves have a CV that increases exponentially with valve position. As the valve opens, the flow rate increases slowly at first and then more rapidly as the valve approaches full opening. This characteristics is often used in applications where precise control at low flow rates is needed, such as a temperature or pressure control. It is the most commonly used type, ideal for maintaining accuracy at low flow rates, such as in temperature or pressure control. Now, these specific CVs values for each of these control valves will depend on the design size and manufacturer of the CV. All right. Now, let's look at the image here. Sorry, this thing is blocking us. But then, if you look at this simple graph here, you notice we have three trends. We have a straight line here, which is the linear type. We have the one at the bottom, which is the equal percentage. You see it will open gradually, and then you see it going up, and then gets to this top. At 100%, you see where it is. Okay, then the CV is going to be 100% at 100% open here, and you see we have the quick opening. So immediately you open the control valve, you see the coefficient is going to just go up, and you see it going up. All right, so this is how the control valve actually functions. So let's go back. So looking at this, so just like I mentioned, we have three characteristics. We have quick opening, we have equal percentage, and we have linear. So depending on the type that we are using for your application, so let's assume we are using quick equal percentage, because that is what we are using in our plant. So at first, when you open the valve at 10%, so at 10%, the flow is going to be minimal, right? Which is why at 10%, we have a lot of fluid coming, but they can't pass through. So there is an accumulation of this crude on the line, and due to that accumulation, the pump is going to be running, trying to push something, but it's not going. And a lot of things are going to happen when at this scenario. So at this scenario, we can have what we call internal recirculation. Internal recirculation is a situation where instead of for the flow to be going forward, to be going out into the pipe, it's going to be recirculating inside the pump shaft. Okay, and with that, it's going to cause wearing. All right. Also, what can actually occur here is overheating. Like we said, while the pump impellers are running, since nothing is going out and we have recirculation inside, there's going to be a buildup of temperature, and overheating is going to take place. I'm going to have also vibration inside the pump, so we don't need that. Okay, so it's very important you understand the opening of this one. So let's close this. All right, now let's look at this chart here. let's look at the chart here. Okay, now this curve you're seeing here is the pump curve with safe and unsafe operating zones. Okay, so here we are going to be talking about operating zones now. Now there is a particular region that your pump should be able to operate and it will be safe, and there is a region that your pump, when operating at that region, is going to be unsafe for the pump. Okay, and above a particular region again, if it operates in that region, it's going to be unsafe. So first of all, let's look at the safe region. So the safe region is within 30% to 115% of your design capacity. Okay, so here, from here down to here is our safe region. Okay, now if you're operating at this capacity, it means your plant is actually operating at the safe region. But anything below this is not good. It's not safe for your pumps. So let's say you are you're operating a plant 30,000 barrel, and then you're operating at let's say 50%. So 50%, your flow rate is going to be what? 0.5 times 30,000 barrel. So you are going to be getting 15,000 barrel per day. Now this is very unsafe. Okay, now what will happen here when you're operating at this capacity? It means your pumps are going to wear with time. Okay, your pump will not be running at an efficient capacity. The pumps might be cavitating at the point. The pumps will be recirculating. Okay, so these are things that we need to avoid. So when you're operating your pump below 60% is actually not safe, and this is the region you're seeing. This is the region you're seeing here. This region is when you're refining below the best efficiency point. So this region is not safe. So for a 30,000 barrel refinery, if you're refining 15,000 barrel or you're refining 18,000 barrel per day, it means you are within an unsafe region. And equally, for a 30,000 barrel refinery, if you're refining above 35,000 barrel, also you are refining at an unsafe region. Now this can cause your pump to actually overload. Your pump motor is going to overload. Okay, so this is also not a good region. So try not to operate at this region. And I believe this decision is made by the plant manager. Okay, you need to advise. The plant manager should be able to advise the management that refining at 60% capacity is not safe for the plant, and also refining above 115% capacity. Well, 115% capacity is not that bad. You can refine up to 125% capacity, but anything above 125% capacity is not acceptable. But within 115 to 125%, that is mechanically safe for a while, but then it should be temporal, not permanent. Okay, so that's that for control valve. So I think we've demonstrated this in our simulator already. Okay, so next let's look at pressure effect. I think I've talked about this already, but just to emphasize more again, when we have high flow, we have less resistance on the pipe. Now when there is less resistance, it means the pressure is going to be reduced. But when there is low flow, when the pump is running and then there is low flow, it means we have a lot of resistance. So that resistance will actually raise the pressure on the line, and this also goes when talking about effect of temperature too. Now the control valve also affects the temperature on the line, which is not good. I think there was a scenario we had on our plant that while we are carrying out a particular operation, we are carrying out an inter-tank transfer operation using a pump. Now, at the point, there was an issue with our air supply, with our air generation unit. Okay, so the instrument air got depleted. Now, once that occurred, the shutdown valve was closed, automatically closed. Meanwhile, the pump was still running. Now, nobody noticed, and then I think after an hour, a field operator was doing an inspection and noticed the pump was very hot. Now, when we go to the pump, the temperature of the pump was reading around 100 degrees. Now, the pump was very hot, that everywhere was, in fact, the casing of the pump was very dark. It was almost like it wants to explode. Okay, so that's the effects of restricting a flow while the pump is still running. So if there is an interlock that can actually trip up the pump when the temperature gets to a particular range, let's say 50 degrees, it will be very good for a trip to actually trip off the pump. But there was no trip on that particular pump, so the pump was running continuously while the temperature was increasing. So any restriction on the line is going to increase the temperature on that particular line. So, and that's vice versa. When there's no restriction, the temperature will drop. When there's a restriction, the temperature will build up and then it will increase. So that's that about temperature. And I talked about the FIQ too, and you see the FIQ is actually calculates the accumulation of the flow on that line per day. Okay, so basically I've been able to touch all the areas that we are supposed to touch for this video, so I don't want to make the video to be too long. Right, so thank you guys for watching, and then if you have any observation, you can drop it on the comment section. If you want to reach out to me, you can just reach out to me, and we can discuss more about my simulator. You can discuss more about the topic. We can share knowledge, and that's that. Okay, so thank you very much. See you in our next video. In our next video, we are going to look at our furnace. We are going to simulate the furnace, and then we'll see how the furnace behaves. Okay, so see you in the next video.